Okay, so I'm going to talk about completeness thresholds for memory safety proofs. And this is a joint work with my colleague Justus Fasse and my PhD advisor Bart. So, and in this work, we study the connection between bounded proofs and unbounded proofs, and we leverage this connection, and we present ideas on how we can leverage this connection to increase the trust that we can put in bounded model checking. And we also try to answer the question of when a bounded proof actually becomes a real proof. Okay, so let's start with a quick example. Model checking is great to find bugs, so let's try to find one. The setting that we consider in this work is a while language with pointer arithmetic, and the only property that we care about is memory safety. Okay, so here you have a very simple program with a bug. So, and we have variable a that is a pointer to an array. We have variable s that stores the size of the array, and we iterate over this array, try to access each element, and obviously there's an off by one error. Okay, so now in order to model check this example, we have to do two things. So first, we have to tell the model checker that we expect that the array is actually allocated and has size s. And we also have to tell the model checker that it should explore arrays up to a certain size bound. Now the question is, well, since we want to find the bug, how big do we have to choose the size bound? And here it's quite simple. The error starts to occur for an array with a single element, so we can simply choose one as size bound. Now what happens if we switch from an off by one error to an off by two error? So in this case, we see that the error starts to occur for arrays with at least two elements. So that means that we have to increase the size bound that we check. So we have to choose at least two as size bound. And in general, it can be quite hard to come up with these size bounds, but this example shows two things. So when you want to model check a program and you have to come up with these bounds, you have to take the program into account that you want to model check, but you also have to take the kind of errors into account that you want to find. Okay, but as I mentioned, model checking is established and great to find bugs, but can we also use it to prove that the program is actually correct? So let's get rid of this error and try it again. So now, obviously, no matter for which array size we check the program, we won't find any problem. But then the question is, well, how big should we choose the size bound to convince ourselves that the program is actually correct and that we didn't just choose the size bound too low? And when you write down such a program, you usually have an intuition of what it does, and you probably here have the intuition that all these loop iterations behave uniformly. And when you model check such a program, you usually have the intuition that since the iterations here behave uniformly, it should be enough to check the program for some small input values, and then it should be possible to generalize the results. And basically, we follow this intuition and try to formalize it and use that to prove that here it's indeed fine to just check such a program for some specific small input values and then generalize the result and get unbounded guarantees. Okay, so let's maybe first take a few steps back and let's take a look at how model checking works for finite state transition systems. So let's say we have a system T, and let's say all the gray dots here that you see are the states that we have to explore. I omitted the edges just to get rid of the noise. And let's say that the property that we want to check is GP. So we have to prove that some property P holds for every reachable state. Now the way that bounded model checking usually works is that we define some depth K, and well, then we basically just explore all path prefixes until we reach this depth K. So you can basically do this for different Ks, and the further you increase it, the bigger the prefix of the transition system that you explore becomes. And that means that larger K in general give you stronger guarantees because you basically looked at a bigger part of the transition system. But you always have to decide for yourself, well, I mean, when you should stop. So basically you have to decide for yourself how big the prefix needs to be to convince yourself that the guarantee that you just check doesn't just hold for the prefix but for the entire transition system, and that's very difficult in practice, so therefore people in the model checking community came up with this concept of completeness thresholds. And in this context, a completeness threshold is a number k with the property that if we know that the formula phi that we want to check holds for the prefix, or holds for every path prefix up to this length k, then we also know that phi holds for the entire transition system. And in general, it's extremely difficult to come up with such minimal k. And therefore, what people did is basically they studied very specific families of formulas and derived over approximations for these formulas, or these families of formulas. And they usually express their over approximations in terms of key properties of the transition system. So for example, if we get back to our property GP, then we know that the recurrence diameter is a completeness threshold. And the recurrence diameter here is the length of the longest root-free path in our transition system. So what does that mean? Let's say that the length of the longest root-free path here would be 5. Then we know that it's totally fine to just carry out a bounded proof up to this depth 5, and if that checks out, then we know that our property does not just hold for that prefix, but it holds for the entire transition system. Okay, so it would be very cool if we could just take this definition and these findings and apply them to program verification. But the problem is that programs, or heap manipulating programs, or programs that process data structures that can have arbitrary sizes, in general do not correspond to finite state transition systems, but in general they correspond to infinite ones. And the problem with infinite transition systems is that all these key properties that we would usually use to describe LCTs can be infinite. So for instance, an infinite system can have an infinite longest root-free path, and that would mean that our completeness threshold here would be infinite, so that would essentially be worthless to us. So that means that we basically have to check for a new perspective, we have to find a new way to look at things. So, and what we basically did is, instead of studying the transition system that corresponds to a program, we study the program verification conditions. And the verification condition here is just some logical formula with the property that as soon as this formula holds, then we know that the program specification that we actually want to prove also holds. So that means that we can verify the verification condition instead of the program. And in general, these VCs are over approximations. So it could be the case that your verification condition is false, even though your spec is correct. So we have to be careful to take this into account. And in our setting, a completeness threshold is a bit different than in the traditional setting of finite systems. So because we are looking at programs and program specifications, and we are looking for a completeness threshold of some variable x that comes with a domain capital X. And the specification then usually has a form for all x in this domain, some formula spec holds. Now for us, a completeness threshold here is not a number k, but is actually a subdomain q of the program variable domain. And this subdomain needs to have the property that if the spec where we restrict the variable x to the subdomain holds, then the unrestricted specification that talks about the entire program variable domain also has to hold. And our approach to verify that a subdomain is a completeness threshold essentially consists of 2 steps. So the easy part is that we take the spec and we automatically generate a verification condition. So the verification condition here has the form for all x in the domain, some formula spec holds, given that x is actually the variable for which you want to get a CT. And then the hard part is the second step. So what we do is essentially we have to manually study the verification condition and come up with a subdomain y for which we believe that as long as we stay in this subdomain, then the concrete choice for x shouldn't affect whether or not our verification condition actually becomes true or false. So then the difficult part is that we actually have to prove that this guess is correct. Okay, so what we basically do is we take our VC, we drop the quantification, so that means that we just look at VC of x, where x occurs freely, and we restrict x to the subdomain y, and then we transform it and basically try to eliminate x. And if that worked, we get a formula VC prime, where x doesn't show up anymore, and that means that we just found LCT. So it means that we can basically, for any memory safety proof, we can basically drop the subdomain y and replace it by an arbitrary representative from this subdomain, and then that's all that we have to check in a memory safety proof. Okay, so that might be a bit abstract, so let's maybe take a look at an example. So this is the program that you saw in the beginning. But here we replaced the left and right bound of the range, which we iterate by constants L and R, and we also replaced the offset by a constant set. Now we are looking for completeness threshold for the array size S, and what we do is first we automatically generate our verification condition. So this here is a very simplified verification condition, but it conveys the idea. Essentially what it says is that you have to prove that for every possible size S, assuming you have an allocated array of this size, you have to prove that the heap locations that you access need to be allocated. So and that's A at index A plus set. Okay, so now that we have this verification condition, we can forget about the program, and the VC is all that we're going to look at from now on. Okay, so remember that essentially if the range of which we iterate is empty, then the program essentially doesn't do anything. So therefore we make up this case distinction here and check what happens if the range is empty. And we see in this case our size is smaller than L plus R, and we see that in this case we suddenly quantify I over an empty domain. So that means that the formula becomes trivially true, and that means no memory error can occur here, so we don't have to consider that in the memory safety proof at all. But we only have to consider sizes that are at least L plus R big. Okay, so in the case that the range is not empty, we know that the size is at least L plus R big, and we can use that to simplify the verification condition. We get one that essentially says, well, assuming that I is in the range of which you iterate, you have to prove that I plus set is within the array bounds. And here you see that S occurs on the left and on the right side, so we can use that to eliminate it, and we get a formula where S doesn't show up anymore. So that means that we just found our completeness threshold, and it's totally fine to just take any size that is bigger than L plus R and check that in a memory safety proof. Okay, so let's try to take this example and generalize it into a general workflow. So what we do is, in general, we always start with our program spec, and then we automatically generate a verification condition. Let's say x here is the variable for which you want to get a CT, then has the form for all x in the domain of this broken variable, some logical formula VC of x holds. So then we have to manually analyze this VC and come up with this subdomain y, for which we believe that as long as we stick to the subdomain, the concrete choice for x doesn't affect the validity. And then from now on, we are just looking at VC of x, where x comes from this subdomain. And then we eliminate x, or we try to do that, and then basically we just have to check whether or not that worked out. So if it didn't work out, that means that we just don't have any new information. So that means that afterwards, when we carry out a memory safety proof, we have to consider the entire domain x. But if it did work out, it means that we just found a completeness threshold, so we can drop the subdomain y, replace it by an arbitrary representative from the subdomain, and that's all that we have to consider in a memory safety proof. And then basically we can just pick another variable and start all over again and get a CT for that, and then so on and so on. Okay, but that's a very manual approach, so that means that it's hard to scale it to complex programs. Therefore, we are currently looking into ways to achieve that, and one way is to use an existing technique called program slicing. So remember, we take our spec, generate a VC, apply the workflow. And VCs have the tendency to become very complex, very fast, so it would be great if we had a way to get a simpler VC. And program slicing allows us to do exactly that, because program slicing allows us to identify the parts of the program, or the core of the program that actually matters to us, and drop the rest. And that means that we can't just consider this core for the VC generation, so we get a simpler VC. We can apply the workflow, and that will be much simpler to do than with the complete program. And another approach to scale is basically to study how the structure of the program affects completeness thresholds. So we call that CT combinators. So let's say that your program is a sequence consisting of two subcommands, C1 and C2, and let's say you already have CTs, Q1 and Q2 for each. Then it's clear that the completeness threshold for the sequence is just a union of both. It's similar for control structures. So let's say our command has the form if E, then C1 else C2. Let's say you already have constraints that describe the CTs for each branch. Then it's also easy to come up with a constraint that describes the CT for the entire if statement. And we can basically use these CT combinators to build up completeness thresholds in a bottom-up fashion. So that means that we start with sub-ASTs that are sufficiently simple. We get constraints describing the CTs for those, and then we apply the CT combinators to propagate these constraints upwards until we get a constraint describing the completeness threshold for the entire program. And as I mentioned, this is a manual approach, so clearly in the future we want to automate that. So that means that we want to find a way to automatically rewrite our verification condition into a form that makes it more obvious whether or not a variable affects the validity of the verification condition. So if you have any ideas of how to do that, let me know. And we also want to demonstrate that we can actually scale this approach to more complex programs and data structures such as lists and trees. And we believe that this work has the potential to increase the trust that we can put in bottom-up checking. Because clearly, if you get CTs for all the variables in your program, then you can easily turn a bounded proof into an unbounded proof and get unbounded guarantees, and that would be cool. But a lot of time that won't work because it's very difficult. But even if you get just a CT for one variable in your program, that allows you to shift computing resources from checking non-critical bonds to checking more critical bonds. So let's say, for instance, that you have a program with two variables, x and y, and normally you would just run a bounded proof up to bound 10 for both. Then this takes a certain amount of time, right? Now let's say that you actually figure out that it's enough to check x up to value 5. So that means that you get two things. So first, you get kind of unbounded guarantees for your variable x, but also you know that now you can decrease your x bound to 5 and your proof will run through faster. So you save yourself maybe a lot of time. And then you can reinvest this time and use it to increase your y bound. And that means that now you get stronger guarantees for y because now you explore more values. So you get a proof in which you can trust more than the initial proof, basically. And so what we did with this work is we presented the first generalization of completeness thresholds to infinite state systems, and we presented a connection between bounded proofs and unbounded proofs for the context of program verification. And while this is foundational research, we believe that it has the potential to be integrated into bounded model checking in the future. Thank you.